Hey, what's up, guys? Yeah. So today I want to talk about uh, an interesting topic called the Arthur Birding protocol, and this is the classical complexity theory, but one can like generalize this into like quantum, into the quantum one. Okay, so sorry, I just misspelled it. Okay, okay. So this Arthur Birding protocol is, I think, it's this one. Okay, so invented by this one. So the idea is that there's a wizard, right? So wizard is the Merlin. So Merlin is all powerful, and the Arthur is like a polynomial Turing machine. Okay, and the idea is that one can define the complexity class where Merlin give some advice to Arthur, and Arthur may have a chance to verify it. Okay, so the complexity class MA. Okay, so MA means that Merlin send a message, message, and the author read it. Okay. And the author is somehow like a probability Turing machine. Okay, so you can imagine that MA is like the mixed type of the mixed type of MP and the BBP. Okay, so let's write down the definition. Okay, so L, a language L in MA, sorry, MA, Merlin author. If there is a polynomial Turing machine, which is polynomial probabilistic Turing machine, let's call this M, and the polynomial P and Q, okay, such that for input with length n, if x belongs to L, right? If x belongs to L, then there is a message that Merlin can send to Arthur, right? So there is a Z, and these messages need to be polynomial type, right? So it's 0, 1, length is, let's say, Q to the n, and the probability that the Y, which is so you imagine that this Y is the coin that the Arthur can flip. So Y from 0, 1 to the P to the N. So M takes 3 inputs. The probability that X, right? So X is the input, and Y is the probability of Arthur. The probability the coin that Arthur flip, and this is the message, right? So Arthur is very happy that Merlin gave a message. That probability that if X belongs to L, then there's a message that Merlin can give Arthur, such that Arthur will agree. Okay, so it's probabilities. Okay, and then F do not belong to L. Then for all Z, the probability of M accept. So this is M out. The probability of M output 1. The probability M output 1 is less than okay. Okay. Yeah. So this is the Merlin author. So the definition looks complicated, right? But idea is that Merlin can send some polynomial size length to Arthur, and the Arthur is probabilistic Turing machine, where Arthur can just can run it. Okay. So obviously that one immediately see the BBP is from MA, right? Okay, the reason is the proof is very simple, right? Because Arthur can solve it. Right? Arthur can solve the problem itself. Okay, so whatever Merlin give Arthur, then Arthur just don't care, right? Because Arthur can neglect this Z, and then Arthur directly solve it, right? By definition, the BBP means that the probability of MXY accept is greater than equal to 2/3. Okay, and obviously that NP is also in MA, right? Because the reason is very simple, because Merlin just need to give the certificate. Okay, so yeah, certificate, right? So if it's MP, then Merlin just give you the certificates, and Arthur is probability Turing machine, and NP by definition, you can verify the answer in the polynomial time. So NP is also in MA. Okay, so this is like one round. One round means that Merlin sent to Arthur, and Arthur need to decide. Okay, and then there's another complexity class called AM. Okay. So AMA is the idea that let me just write idea. So idea is that the author sent to Merlin some flip some coins. So there's a flip a coin. Okay, and then Merlin just give you author some advice, right? Some answer. Then author decides. Okay, so simply speaking, the same definition. If X belongs L, then we must so probabilistic that okay, so now the Merlin so author flip coin, right? So author flip coin, so author 0, 1 to the P to N. And then there is a Z belongs to 0, 1 to the Q to the N, right? So given author has probability and the Merlin give this message to author, there is this Z, right? Such that M of X, Y, Z output 1 is greater or equal to 2/3. Okay. And then if X do not belongs L, then the same thing, the probability of 0, 1 to the P to N. Then for all Merlin message sent to author, that the Merlin cannot cheat author. So output 1 will probability less than 1/3. Okay, so hopefully this is makes sense, right? So author send the flip coin to Merlin, and the Merlin just send back some strange message, and author decides. Okay, and and you can define yeah. So this is called A. Okay, and from this that you can define like more, like you can just write down all the definition, right? So you can write down the MA. Also, so MA means that Merlin send author, also AM that author send Merlin, and the Merlin send something to author, then author come back, and then we can define an idea called the MA. You can define an idea that Merlin send to author, right? And author feel like some strange, and since there's a Merlin, and the Merlin just send some back to author. Okay, and you can define something like, and you can just keep going. Okay, define something like this. Okay, and so the usual definition is that yeah, one can define an idea called AMK. Okay, so AMK, you can imagine that AMK is just, simply speaking, just K rounds for any author. Okay, and if you don't fix K, you assume that one can do AM but polynomial rounds. Then you can define this is what we previously proved. This is called interactive proof. Okay, and the famous result is interactive proof is equals IP equals to P space. Okay, and okay, so fact, maybe one non-trivial fact that I didn't show up here, basically is the MA is the subset of A. Okay, and the MA is also in the PH and also in the P space. Okay, and yeah, so this is what I want to prove here. All I want to explain in this video, and the graph non-isomorphism is famous that somebody give you two graphs, right? And you ask Merlin whether these two are non-isomorphism. This problem is in this graph non-isomorphism problem is in the Arthur Merlin. Okay. Okay, and also some non-trivial fact is that MA is the subset of PP. Okay, so yeah, this is the Arthur Merlin protocol definition. And before I finish, I want to define an idea called the quantum Merlin Arthur. This is also a famous complexity class called the QMA. There are a lot of things I want to say, but let's just give it a definition. So now you imagine that, right? You imagine that the Merlin still like all powerful, right? So Merlin is all powerful. But Arthur is it's not just classical one, but Arthur has a quantum computer. Or simply speaking, that Arthur is a BQP guy. So Arthur can like solve the BQP by itself. Okay, so language L in a QMA, right, if you satisfy the following, and there's a polynomial P, right? So such that if X belongs L, Then there is a quantum state, right? So Merlin can give the quantum state to author, such that the author, the probabilistic, so let me just forget about those. So the probability that the author verifier accept with X and psi. So author can have the advice, right? Author can give so author receives some state psi, and author can just run a probabilistic machine. But this big P, right? So the probabilistic author read this quantum or some strange initial states and X. The probabilistic that the author accept is greater or equal to 2/3. Actually, you can just change it to some constant number. Okay. And then you can also define X belongs to L. Then for all states that Merlin sends, the author will reject with high probability of one less than 1/3. Okay, and then you can define idea. Basically, this is the quantum Merlin author. Okay. And then there are some problems called the QMA complete, means that this problem is hard. Okay, and obviously that QMA is a subset of QMA. Yeah, I think let me see where there is something I want to say in this video. Okay, I think that's enough. See you guys next videos.